for any device utilization. But here in my talk, I especially talk about a theoretical calculations, which is maybe very far from the application that we are looking in the morning. So I will be using a quantum mechanics here. I'll tell about what is quantum theory and all. My talk will be decided on 4 parts. I will be rushing very quickly, but however, I will be available through online. You can always catch me through my email address and pose any question that you would like to have. Yeah. So quantum theory is a basically we will use approach which depends on the quantum mechanics to explain the physical properties of any material. So this is a quantum theory. Okay. And if you see any material as a function of the temperature, there are different phases that we have. For large temperatures or very high temperatures that we see the plasma phase, and the very low temperatures we see condensation and the solid, and that's where actually quantum is going to work. So the other name of this field is called low temperature physics or low temperature theory. In a nutshell, the quantum mechanics is we use uncertainty principle saying that we don't simultaneously determine position and momentum. It is impossible. So we need to take an approximation. Of course, we deal with the wave functions and also the superposition of the states. This is what exactly anything that material exists, this is going to be happen. There should be overlap of the states to form a molecule and any other functional materials. Result of that, we actually see the close interactions between the atoms. Those are represented with the symbolic letters such as T, U, F, lambda and J. So the J is a magnetic exchange, T is a kinetic hopping, and the U is a Coulomb interaction, lattice geometry, dimension of the function as structure factor, and the spin orbit coupling. So based on this quantum mechanical phenomena that we occurred between the two atoms and the electrons interaction, we actually see the direct application in the day-to-day life, even before that the phenomena of the quantum that we have to deal with or understand, that like multipolar ordering, quantum liquid crystals, quantum order or disordered magnets, or unconventional high TC superconductors, topological protection, correlated insulators, fermions or non-fermion liquids, and charge spin density wave phases. So all these are found to be very different. You may be thinking that I'm talking some different language that you don't know ever. But however, these are the theory background needed for any application to be utilized in forthcoming future. So the application is we will have a low energy cost energy harvesting. That means we will be spending very less energy to harvest the energy. And the effective electronics or the spintronics, one of the application today morning Professor Bhatnagar was mentioning, the spintronics can take over several devices. And the information technology, the quantum information that we are talking about now, the present day government is more interested and curious to know how to develop this information technology, and a lot of funds has been given to that, and quantum magnets and etc. and other. So altogether, we actually can keep a phase diagram here. This wonderful nature physics paper, you can understand how all those physical phenomena can be understood. Let's see, we know that in 2010, everybody was surprised that the Nobel Prize was given to the product of a pencil. Okay, that is nothing but a graphene. So if you take a graphene or extract a graphene laying from a cellotape and see with the properties of its electrical conductivity, this to be very amazing, and that has led to open up to have different device applications that we are seeing now in this world. In 2010, the Nobel Prize was given, and the lecture was showed that we will be having a different kind of applications such as touch screen, microelectronics, composite materials, tablet computers, solar cells, watches, smart watches, thin flexible light panels, mobile phones, electronic payment. This was proposed in 2010 and now we are in 2023 thanks to the engineers. They have all developed all these things which are proposed in 2010 in a Nobel Prize lecture. It's not because of the nanotechnology, but this Nobel Prize has given an idea that we can think or we can design our own electronics in a different perspective to have a maximum utilization of these electrons. However, the utility of the material can be depend on its basically the tunability. If all of a sudden one of the scientists says that I have found wonderful material that can be solve all the properties of the world, so but that doesn't end there because one should know how it can be tunable for any device that to be utilized. Take a simple example that we have been listening about the silicon devices that we have in our hand. So this was proposed, the design in 1963, 1961, almost 80 years back. So this was the design. Engineers was proposed it and successfully designed some of the electronic devices. But if you see the presented electronic devices also form a similar mechanism but in a different entire architecture that depend on the properties tunability. As one example, the memory device, which was almost 16 square feet, okay, or 100 kg device, which can store only one file, is scaled down, that is sitting in your pocket, maybe in your hand, to store thousands of photos without having any problem, without having generating any heat or any issue at all. So that all because of the tunability of the properties. So the tunability of the properties basically depends on several ways, okay. To get a microchip in your computer or in your mobile phone, so there are so many phases that has to pass through. So they have to go through very thin kind of wafers, masking, etching, doping, and also final testing. After the testing passed, then only the microchip is will be given for a device. So all of them are important for material tunability. So the functionality of a material depends on its tunability. Means any material that to be used for a device application, you should have a tunable properties. It may be structure, it may be composition, it may be physical parameters and electronic parameters also are properties. Before I'm going to proceed further, I'll be working on a 2D magnetic 2D layers or two-dimensional materials which are different from the bulk materials. So I cannot pass through unless I discuss about the graphene. Graphene is a very simple material which contains only two atoms in the unit cell, which are two sublattices, can generate these very thin lines, that lines that you're seeing at this cross section of the energy and the momentum. These lines actually are showing 10,000 times greater conductivity of the silicon. So that was the wonder that people think about the graphene. But graphene doesn't stop here. It also forms a monolayer, bilayer, graphene nanoribbons, and other kind of thing. That opened up other direction. We can explore things in the two dimensions, and that explode in a different two-dimensional materials, especially in the chalcogenides or heterostructures, and all those two dimensions have given a flexibility structure-wise. They can tune to form hybrid materials. We call as the heterostructures or 2D materials by making a monomer designs or assembling them and control their various properties like electric or conductivity and other properties. The core and advanced quantum mechanical methods are the tools to study the quantum theory of any functional materials. So the quantum mechanical methods have a two directions. One is wave function. We generally learn in the textbook, and the electron density is an advanced quantum mechanics that we learn to do any advanced research work in the quantum materials. So especially I would like to go through the what are the density functional methods that to be used for the understanding the quantum theory of the functional materials. So we use the Ab initio theory based first principle calculations, many body tight bending and many atomic simulations, large scale applications. So this is the history, and one of the well-known theory introduced by the Hunberg, Kohn and Cohensham in 1965 has won the Nobel Prize in 2008 by generating a computer code that can help you to understand the properties of the material even before you synthesize in your lab. So that is a wonderful, and that's why it won a Nobel Prize in chemistry. And that is the code that I'm going to use. And it need minimal that you need a computer, and you need some models, unit cell models and physical approximations in the numerical methods, and simply you can substitute, send the commands in the computer using a code designed on the Cohen-Sham wave equation. Then you can understand the properties of the materials. So let me talk about the graphene here. And the graphene has the two sublattices. If you write a Hamiltonian for this one, it's like a 2 by 2 matrix, which is very small matrix that can produce the dispersionless bands near the K points. That tells about the mobility. The slope of these bands actually tells about the mobility of the electrons, that how fast that can behave. Let me give you the real-time example, saying that if I take a mobile and if I touch it, suppose if it has taken 1 second to open an app, the moment you say that I don't need this mobile, the moment when you touch it, if it is opened in a microseconds, then you say that this device is need for me. So that is the fastness, is basically depends on the mobility of the electrons. So this is the hypothetical way of connecting the two applications of the materials and to the real-time applications. So the mobility of the electrons is very important for a fast device applications. So this is the other way of constructing the Hamiltonian for the bilayer, and using this ab initio methods, okay, one can also simulate molecules which are having many number of atoms. So in the beginning of this today's session, we understand that the nano is very small to imagine, okay, but the materials that we are seeing from our eyes, those are containing many atoms. So the quantum mechanics doesn't help you to understand that properties. So to understand that one, we need to combine ab initio and the classical mechanics together and form a force fields and see how a materials can behave. So here is one example that when you compare this quantum mechanics and the classical mechanics and see the two graphene layers when are twisted on top of each other, as they increase the temperature, you see there are a lot of curvations that we have seen. As in the pandals, you are seeing that those tents are getting like this, right? But as a function of temperature, they actually get straight. So this is the how the materials are behaving as a function of the temperature. How to simulate this one? We need a new methods that we need to come with. So far we have learned about the quantum theory, functional materials, and also learned about the methods. So now we go to the gate tunable topological flat bands and 2D layers. So far I have introduced the methods that can be used to understand the properties of the materials. And the new breakthrough of the graphene that I'm going to tell about here is, if you take the graphene subjected to a strong magnetic field, you see the conductivity has become at the step size, it is not continuous. So if I take the same graphene and partially filled, if you give the magnetic field, you see the electronic states near the charge neutrality has becoming a flat, thinner and thinner, and that are responsible for the hues properties or exotic properties of the material. Especially we have more number of electrons for any small energy range that is used for fast device applications. In other way around, if I take the graphene and placing a boron nitride with the rotational alignment, you can see there is some patterns that are happening. You still need a magnetic field to see these flat bands here. But however, in the recent 2018, it was said that if you take the two graphene layers and rotate them or have a small misalignment or orientation, you start see a flat band here even without magnetic field. So without any magnetic field or external stimuli, you can see a flat band that can be used for the device applications. So this has been proved not only just twisted bilayer graphene, but graphene aligning and the boron nitride with a few layers and other chalcogenide materials which are having a different applications. And the fundamental application out of this flat bands is the harvesting the superconductivity. So you see, upon the carrier doping for this twisted bilayer graphene and graphene that is aligned and boron nitride and the transition dichalcogenides, upon the few carrier doping, you start seeing the superconductivity. That means the resistivity getting dropped in the conduction. So how to understand this superconductivity in the 2D materials? So if I take the electrons that are sitting in this square lattice and allowing saying that they can hop from one side to the another side with a hopping energy and also can have a double occupancy like this. The moment under the external stimuli saying that if they are not able to have a double occupancy here, then the each electron that can move or hop from one side to the another side become highly correlated. So this is a strongly correlated situation in any electron that can happen here. So in that case, if you start giving any additional electrons, so that will transform from this pattern to the other pattern where a collective arrangement of the electrons, which is a disorder in nature, there is a transition from order to the disorder, and that can lead to some of the external, some of the exotic properties such as like superfluid, and that may lead to the unconventional superconductivity and quantum spin liquids. Like this, as we have seen the twisted bilayer graphene, we can we can twist other layers also, like you can just twist two of them or you can twist one of the layer on top of the two layers, like so many combinations you can take and see, and it has been proved that even multi-layer graphene can give you the superconductivity and other exotic properties like topological. So within the short time now I'm going to proceed saying that other properties of alternative twisting of the twisted bilayer graphene and combination of this thing also have shown the resistivity drop and the superconductivity. So the fundamental mechanism that happening in this graphene and boron nitride is basically if I take the two graphene layers, their bands have shown they are linear in the nature. The moment when I couple them at a small twist angle, what happens? These bands which are close to the charge neutrality are getting coupled. And whereas if I take the two twisted bilayer graphene and the bilayer graphene, when I twist them, so they also get coupled. But upon the perpendicular electric field here, these coupled flat bands never get isolated. But whereas here in the bilayer graphene and the bilayer graphene, they get decoupled, and these particular band can be accessed by gating the graphene layers, and you can see the superconductivity here. So with this, I would like to further continue saying that we need a different theory to understand this Moore superlattices, eventually to understand superconductivity in the 2D materials. So we need a new approaches of understanding, and that need developing a new theory. So with this, I conclude my talk, and thank you very much for this wonderful opportunity, especially Malapati Venkaya and the Vignans for organizing this conference.
Yeah, thank you.